Hey folks, welcome to another set of Chemistry 2 video notes. In today's video, we're going to learn about equilibrium. This chapter includes 7 sections which talk about the concept of dynamic equilibrium, why reactions reach equilibrium, what the equilibrium constant is and how to write its expression, Le Chatelier's principle, how temperature can affect equilibrium, how to write equilibrium expressions for reactions with different states of matter, and how to use the equilibrium expression to calculate solubilities and concentrations. Let's get started. As we've seen before when we talked about vapor pressure, when a reaction can go in 2 directions, forward and reverse, and the rates of both of those reactions are equal to each other, our system has reached what's called dynamic equilibrium. If we think about water evaporating in a sealed flask, some of that water will turn into a gas. That's the forward reaction. As we get more gas molecules, some will turn back into a liquid. That's the reverse reaction. At some point, the speed or rate of the forward and reverse reactions will end up being the same. At that point, the total amount of gas molecules no longer changes because we're creating them as fast as we're using them up. At that point, our reaction is said to be in dynamic equilibrium, and the pressure caused by that constant number of gas molecules is called the vapor pressure. We call these equilibria dynamic to help remember that reactions are still happening in both directions. They're not stagnant. It's just that since reactants are turning to products at the same rate that products are turning back to reactants, it looks like nothing is changing to us. Once the forward and reverse rates become equal, the concentrations of reactants and products stop changing, whether or not the amount of reactants and products are equal to each other. Go ahead and get that in your head right now. Equilibrium does not mean equal amounts of reactants and products. This equilibrium could occur when the reactants have a higher concentration than the products, and we call that reactant favored, or we say that the equilibrium lies to the left. If the products have a greater concentration at equilibrium, we call it product favored, or say that the equilibrium lies to the right. As long as there's a significant concentration of both reactants and products at equilibrium, we consider a reversible reaction and use a double harpoon arrow like this for our reaction arrow. If the reaction falls so far to the left that hardly any products are ever formed, we say that the reaction does not proceed. If it falls so far to the right that almost all of the reactants turn into products, we say that the reaction goes to completion. You might be wondering, why do reactions reach an equilibrium? Easy. If we know about how reaction rates work, which we should since we just did chapter 13, then we just have to apply that concept to understand equilibrium. As a reminder, reaction rates are dependent on the rate constant, controlled by temperature and the addition of catalyst and other things, and the concentration of the reactants. So when we perform a reaction in the way that we've been thinking about them, in the forward direction, we start with some amount of reactants and no products. When we mix those reactants together, they are at the highest concentration they will ever be. Therefore, the reaction happens the fastest at the beginning, because as you remember, the higher the concentration of your reactants, the faster your reaction goes. As those reactants get converted into products, the reactant concentrations go down. They decrease. Since the reactant concentrations are decreasing, the rate of the forward reaction also decreases. Now, if we take that concept and flip it on its head, we can understand what happens in the reverse reaction as well. If our reaction is reversible, as we make products, some of them will turn back into reactants. This starts off really slow because we start without any of our products at all, and then we only have a little bit, so the rate of that reverse reaction is slow because we only have a little bit of those products. As our reaction starts to create more and more of that product, the concentration of the products get bigger, and so the rate of the reverse reaction gets bigger. To summarize, as we start a reversible reaction with only reactants, as one normally would, the forward reaction starts off fast and then slows down, while the reverse reaction starts off slow and then speeds up. At some point, the forward rate and the reverse rate finally meet somewhere in the middle, and they no longer change. This is our dynamic equilibrium. As you can see here, each of our reactions, both the forward and reverse reactions, have their own forward and reverse rate laws. and thusly they have their own forward and reverse rate constants. We may find ourselves in a situation where we need to know the equilibrium constant of a reaction in dynamic equilibrium. The equilibrium constant is nothing more than a ratio of the forward rate constant to the reverse rate constant. The easiest way to determine the equilibrium constant is to find the concentration of each of your products and reactants once the system has reached equilibrium. You then plug those concentrations into the KEQ expression. The KEQ expression is made similarly to the rate law of an elementary step in a reaction mechanism, but we put the product concentrations to the power of their coefficients divided by the reactant concentration to the power of their coefficients. So it's a fraction. You have products on top, reactants on bottom. We'll talk more about the derivation of this expression when we do our Jamboard together. The important thing to know about an equilibrium constant right now, though, is that it can tell you whether or not your reaction occurs, if it lies to the left, if it lies to the right, or if it reacts to completion. If the KEQ is less than 0.001, it suggests that your reaction barely converts reactants into products, and we say it does not occur. If it's greater than 1,000, we say it goes to completion because almost all reactants turn into products. If it's somewhere in between, it's at an equilibrium. The equilibrium lies to the left if the KEQ is less than 1, and it lies to the right if it's greater than 1. If the KEQ is exactly 1, we say it's in perfect equilibrium, and the reactants and products have the same concentrations at that equilibrium. Now, once a reaction has found its happy place, or its equilibrium, you can try to tip the scales a little and make it proceed more one way or the other. If you disturb that equilibrium, it'll do whatever it needs to do to return back to the same KEQ value. For example, if you have a reaction of sulfur dioxide and oxygen producing sulfur trioxide with a product's favored KEQ of 810 at equilibrium, a good portion of reactants have turned into products, almost all of them actually. Perhaps you're able to remove some of the O2 reactant in this equation. In order to help replenish that loss of O2, the SO3 will convert back into O2, so the reverse reaction will increase, creating more SO2 in the process. Your SO3 concentration will go down a little, your SO2 concentration will go up, and your O2 concentration will go up a little bit from where it was after you removed some O2, but not quite all the way back up to where it was before you removed some O2. If you added more SO2 to the reaction on the reactant side, the equilibrium would push back to the right to help get rid of that extra SO2. The basic principle is that whatever you do to the equation at equilibrium, it'll try to cancel out whatever it is that you did. If you add more of something to the left, it'll push to the right. If you take away something from the left, it'll push back to the left. In its essence, this is what's known as Le Chatelier's principle. Le Chatelier's principle applies to temperature as well. If you have an endothermic reaction, that means you have to add heat or energy to your reactant side to get it to go. If you raise the temperature, the reaction will push to the right to relieve that extra heat on the left side. If you bring the temperature down, the reaction will push to the left to replenish some of that heat that you took away on the left side. For exothermic reactions, heat's on the product side because energy leaves the system. So it does the opposite. If you add heat, it pushes to the left for exothermic reactions. If you take away heat, it pushes to the right. As we said before, to find KEQ, you simply put the products to the power of their coefficients multiplied together over the reactants to the power of their coefficients multiplied together. This works when all species in your reactions are gases or aqueous. If you have solids or liquids, it doesn't quite work. Pure solids and liquids do not get included in the right side of the KEQ expression because their concentration essentially doesn't change. We don't really ignore them, but since they are constant, they get included in with their equilibrium constants for the reaction. For solids and liquids, we would measure their concentration as grams per volume of a substance, which is density. And as you know, any pure substance keeps a constant density at a constant temperature, no matter what happens to it. So even though the solids get used up in a reaction, since their density doesn't change, we say their concentrations don't change. The math shown here is the mathematical reasoning for why we can ignore solids and liquids in the K-eq expression. Pay attention to our Jamboard or read that section of your book for a better explanation on what that math is saying. The very last, but frankly one of the most useful things we're going to talk about is the solubility product, known as KSP. While we learned solubility rules as black and white, it either dissolves or it doesn't, the fact of the matter is that most things do dissolve to some degree. It's more of a gray area. If they only dissolve a little, we would consider them insoluble, and if they dissolved a lot, we would consider them soluble. As it turns out, there's a range of solubility, from insoluble to sparingly soluble to mostly soluble to completely soluble. The KSP can help us determine just how soluble a solid compound is. The KSP is basically an equilibrium constant, specifically for dissolution reactions. The larger the KSP, the more the substance dissolves. Since the reactant for a dissolution reaction is always a solid, because that's what you dissolve, a solid, the KSP expression only includes the products and can be found by taking the ions that our solid turns into, taken to the power of their coefficients, and multiplied together. Knowing this expression, if we know the value of KSP, we can do a little bit of clever math to determine the solubility of a substance. Since the KSP is an equilibrium constant, and a solution is considered saturated once it's reached that equilibrium, then the KSP can tell us just how much of our solid we can dissolve before we get saturated. To find this, you just plug in the relative concentrations of each ion as a value of S, 1s, 2s, 3s, etc., based on the coefficients from the balanced equation. You plug those S values into the KSP expression and then solve for S. This tells you how many moles per liter you're able to dissolve. You can leave your answer as is or convert the moles to grams using molar mass, and then you get the common unit for solubility, which is grams per liter. Well, that's all for today, folks. Look forward to our Jamboard session where we cover multiple examples of the math behind these concepts. As always, if you have any questions, let me know.